In this video, we're going to explore one other possibility that can appear when you are trying to do a partial fraction decomposition. In this case, we're going to look at the situation where one of the pieces of the rational function that you're trying to break down contains a quadratic that has no real roots. So this is a situation where the denominator doesn't factor fully into linear factors over the real numbers. But you end up with these quadratic factors that kind of stick around. What I'd like to do to start out is to kind of show you the basic shape that we're going to be building off, the basic format that you use to look at the partial fraction decomposition, and then we'll do an explicit example. So let's suppose that we've got a rational function. Maybe we have a polynomial in the numerator, say x plus 1 or something, maybe x plus p, keep it a little bit more general. And in the denominator we have perhaps a linear factor, x plus q, and then a quadratic factor which we're going to say has no real roots, can't be factored any further. So we'll just write that in general form, maybe x squared plus little bx plus c. And we'll say that that doesn't have any real factors, okay? So if we have a rational function like this, if we're going to propose a partial fraction decomposition, the linear factor is treated the same way it would be if I just had linear factors. It gets one term with a constant divided by that linear factor. But this quadratic factor, if it doesn't have any real roots, it turns out that to cover all our bases, we're going to need to introduce two different amounts or two different pieces to the piece that we put into our partial fraction decomposition. So what we'll need is we'll have that quadratic will be in the denominator, x squared plus bx plus little c. And in the numerator, we're going to put a linear function. So we're going to put maybe b times x plus c. And this is a capital C, different than the part that's appearing in the quadratic. So these capitals and lowercase numbers are just different in general. Okay, so this is how we're going to deal with our quadratic factors. We're going to introduce a linear function in the numerator. And that, it turns out, will cover all the situations that we need to worry about when we try to break this thing down into its component parts. All right, so let's use this shape or this idea to deal with an explicit example. Let's look at maybe put x plus 2 in the numerator, and we'll put maybe x plus 1 as a linear factor in the denominator, and we're going to put attached to that a quadratic that doesn't have any real roots. So how about x squared plus 9? That won't have any real roots. When I take any number x, if I square it, that'll make sure it's positive. So if I'm adding 9 to that, it means that x squared plus 9, that can be never be equal to 0. So it never has any roots there. Okay, so this is our big rational expression. If we're going to propose a partial fraction decomposition for this, we need one piece for each of these, the linear factor, and one piece for this quadratic with no real roots. So we're going to break this down as a, which we need to find, divided by x plus 1, that linear factor that appears in the denominator. And then this quadratic, x squared plus 9, since that doesn't factor any further, we're going to include a bx plus c in the numerator. Okay, so it's a second degree polynomial in the denominator, and we're allowing a first degree polynomial in the numerator. Two separate pieces that we're going to try to find. Alright, so this is our shape for our partial fraction decomposition. Once we've proposed this shape, it's identical. The process is the same as the other situations with the denominator. So we want to convert to a statement about polynomials, and then to select a series or a sequence of x values that give us very, very simple information about the values of a, b, and c, which we're trying to find. Okay, so we have the big thing, breaking it down into smaller things, and then we want to figure out the right amount so that the decomposition that we propose is actually equal to the expression that we started with. So we've proposed our decomposition, we've dealt with this quadratic with no real roots, And what we want to do is now get rid of all the denominators. So we multiply by the denominator on the left-hand side, and that'll remove all the denominators since all the pieces of the decomposition are built from parts of that denominator. Right, so we convert this into a polynomial statement by multiplying by x plus 1 times x squared plus 9. Multiplying both sides by that, our left-hand side, the denominator cancels perfectly. And on the right-hand side, parts of the denominator cancel and other parts will be left over. So when I multiply this first term by x plus 1 times x squared plus 9, the x plus 1's cancel and we're left with x squared plus 9. So we get a multiplied by x squared plus 9. And then in the second term here, we're going to multiply by x plus 1, x squared plus 9. The x squared plus 9's cancel and the x plus 1 is left over. But now my numerator has two pieces, bx plus c, so we're going to have to worry about multiplying those things together. So we have bx plus c multiplied by this x plus 1 factor that's left over. Okay. So now we've got our statement about polynomials, and we need to substitute in enough values of x, enough different values of x, so that we get information about the values of a, b, and c. Just like before, we want to select values of x that are going to simplify our life, make the algebra as simple as possible. So the only value of x which is going to completely remove a's, b's, and c's is the value of x from this linear factor, x plus 1. So I want to choose that as one of my values. Another thing that might help the algebra or might simplify the calculations a little bit would be to choose x equals 0. X equals 0 will remove the b term. But that's only two values of x to try out. We still need to pick a third value of x so that we'll have enough information to get the values of a, b, and c all separately. Okay, so let's proceed and work our way through this. We'll start out with x equals -1 because that's going to remove the b and the c, and that'll tell us something about a. So we choose x is equal to -1. If I substitute that on the left, I get -1 plus 2 is +1. I substitute x equals -1 into the coefficient of a. I get -1 squared is going to be +1 plus 9. So I get a multiplied by 10. And x equals -1 sets this factor equal to 0. -1 plus 1 is 0. So all of this stuff drops out when we try x equals -1. So that first piece of information tells us, if we divide both sides by 10, tells us the value of a. A is 1/10. Okay, so that's a little bit of progress towards the solution. Next, maybe we can try the value x equals 0. That'll remove the b term. X equals 0. And substitute that in everywhere in this expression. We're going to get 2 on the left-hand side. A times 9. So a is 1/10. You know that. And then 0 plus 9 is 9, so that's 9/10. And then x equals 0 makes the b cancel out, so we get plus c multiplied by 0 plus 1 is just 1. Okay? So this value of x now gives us an equation that we're going to need to solve for c. So we might write this thing in terms of, say, a common denominator, so we can do the algebra. We have 20 divided by 10, getting a denominator of 10 on the left-hand side. We have 9/10 on the right, and then c times 1 is just c. So I have 20/10 is equal to 9/10 plus c. If I subtract 9/10 from both sides, I'll get the value of c there. So c is 20/10 minus 9/10. We should be left with 11/10. Okay. So now we have the value of a, the value of c, but we don't yet know the value of b. So we're going to need to plug in one more, choose one more value of x to help work out what's going on with the value of b. I think I would choose x equals 1, +1 rather than -1. It's a pretty simple value of x, and it should make the arithmetic relatively easy to work with. You can choose another value of x if you think you can find something that'll work out nicely. Another choice might be to choose x equals -2. That would make the left-hand side equal to 0. So there's lots of different options. But I'm going to choose x equal to 1 as a third value of x and use whatever information that gives me to figure out the value of b. So let's try x equals +1. On the left-hand side, we get 1 plus 2. So that's going to be 3. A times 1 squared plus 9, that's going to be 10. So A is 1/10. And then 1 plus 9 is also 10, so that's 10 over 10. That's nice and simple. We get x equals 1 here, so we get b plus c, and c has the value 11/10. And then this term here, x plus 1, x is equal to 1, that's what we're substituting in. So we get b plus 11/10 times 2, multiplied by the number 2. Okay? Now let's work out the algebra here and figure out the value of b. So we're going to simplify and then solve for b. Get b by itself on one side of the equation. So this term here, 10 over 10, that's equal to 1. So we get 3 is equal to 1 plus, I'm going to reorder these a little bit, 2 times b plus 11/10. It looks like we can do some of the algebra here without resorting to fraction notation to get us most of the way towards b, and then we'll need to deal with fractions near the end. So let's get rid of the thing that's furthest away from b, move everything to the other side of the equation. So let's subtract 1 from both sides. We get 2. 3 minus 1 is going to be 2. That 1 is going to cancel because we're subtracting 1 from both sides. So 2 is equal to 2 times b plus 11/10. And now I'm going to divide both sides by 2. And that will bring me to work up here. 1 is equal to b plus 11/10. And then let's subtract 11/10 from both sides, so we'll need a common denominator. So think of this as 10 over 10 is equal to b plus 11/10. So I want to subtract 11/10 from both sides. So I get 10/10 minus 11/10. I'll be left with minus 1/10 is equal to b. Okay. So that gives me the value of b, the value of c, and from way over here, the value of a. As soon as we know the values of each of these amounts, we've completed the partial fraction decomposition. We know how to split this complicated rational expression into these smaller pieces. Okay? So this basically completes all of the different possibilities that you might see in the denominator when you're trying to do a partial fraction decomposition. Let me wrap it up by reminding you of what those possibilities are. So when you have a rational expression, you might see things that look like linear factors. You might see repeated linear factors. Or you might see things like x squared plus, how about r squared, quadratics. With no real roots. Another term for that is called an irreducible quadratic factor, right? And the numerator here, it could be just a constant like 1 or 2 or 5, or you could have a polynomial in the numerator. That's also a possibility. So maybe this looks like x plus m, or x squared plus mx plus n, something like that. The actual structure of the numerator isn't really important for partial fraction decomposition. It plays a role in our algebra to figure out the amounts, but the real driving force in partial fraction decomposition is the factors that appear in the denominator. Those tell you the pieces that you want in your partial fraction decomposition. So remember that when you see just a linear factor, x plus or minus a number, raised to the first power, that's going to force you to introduce one term in your partial fraction decomposition, which you might write as a over that same linear factor, x plus p, whatever that happens to be. When you have a repeated linear factor, you're going to introduce one piece for each power of that factor. So if I have x plus q squared, I'm going to introduce one term for x plus q, and then another term for x plus q squared. So the more times you repeat a linear factor, the more terms you want to include into your decomposition. The final kind of thing you might see in the denominator might look something like x squared plus r squared. That's an example of a shape of polynomial that has no real roots. When you have a quadratic that doesn't factor, an irreducible quadratic factor, that forces you to introduce, say it's x squared plus r squared maybe. You would introduce two different constants, two different terms in the numerator, one attached to an x and one plain constant term. Right? And that would be the kind of partial fraction decomposition that you would propose for a huge complicated rational expression like this. Right? Once you've proposed the partial fraction decomposition, the next step is going to be to multiply by the denominator on the left-hand side. You can save yourself a little bit of work with the algebra here because you know that when you multiply by this denominator, it will be removed from the left-hand side. So you don't really do any work on the left. You just multiply by the denominator, and in the next step, all you see is the numerator. On the right-hand side, you have to figure out, when you multiply both sides by that denominator, which parts cancel out in each of the terms that you've created. And when you do that, when you work out all that algebra, you end up with a statement about polynomials. As soon as it turns into a statement about polynomials, if you want them to be identical, you just need to make sure that they intersect or agree in a sufficient number of points, in the right number of points. And what you'll need is you'll need them to agree at enough points so that you can figure out the value of each of the parameters in your partial fraction decomposition. So in this case, in this particular example, we have 1, 2, 3, 4, 5 parameters. So we would need to select 5 different values of x in that polynomial equation that we could use to get information about each one, excuse me, about each one of these parameters. Okay? You want, when you can, to cherry pick the values of x that make one or more factor equal to 0 when you're looking at that polynomial. That'll just make your life easier. Once you run out of those sneaky values of x that simplify the algebra, pick whatever values of x you want. As long as they're different, as long as you can work through the computations, you will get information about these parameters. In really complicated problems, you might have to solve a system of linear equations to figure out A, B, C, D, and E. But in most of the cases that you'd see at the high school level and at the introductory college level, if you use the strategy that I recommend, there'll be very little actual algebra that you end up having to do. Okay? So that basically completes the idea of partial fraction decomposition. You're going to break down a big rational expression into smaller component parts. The parts you propose are based on the factors and the kinds of factors that you see in the denominator of the rational expression that you start with. Once you've got your partial fraction decomposition proposed, convert to polynomials, use values of x that give you simple information about the amounts of the different parts, then work out the details. Figure out exactly what the value is of A, B, C, D, and E, or however many parameters you see in the problems that you're trying to solve. Okay? That's the basic idea. And surprisingly, this process is used quite often in more advanced mathematics. It's very helpful to take a big complicated expression and break it down into smaller parts so that you can use simple techniques to handle those smaller parts, be it with integration in calculus or looking at inverting Laplace transforms if you're doing signal analysis type work. Okay? All right, so that completes this video.